Welcome to the session. I am Seshavidya, working as Associate Professor in the Department of ECE at R.M.K College of Engineering and Technology. So in this session, here we are going to discuss about transmission lines and RF system. In that we are going to discuss first unit. So in that first unit, we are going to discuss what is transmission line, what are the types of transmission lines, and what are the primary and secondary constants. So before going into this unit, first let us discuss what is the objective of this subject and what should be the outcome from this. So the objectives. So in the transmission lines and RF system, so these are all the objectives. That is to introduce the various types of transmission lines and its characteristics. And from the second unit, we are going to understand what is high frequency line, what is power and impedance measurement. And from the third unit, we can able to know what is that impedance matching and how to solve the how to just make the impedance matching using Smith chart. That is about your third unit. And from the fourth unit, we are going to introduce passive filters and basic knowledge of active RF components. And from the fifth unit, you can just get the that is a knowledge about RF system transceiver design. So this is about the objective of this subject. This is about your syllabus. So unit 1, which deals with the transmission line theory. Second unit deals with the high frequency transmission lines. Third unit is about impedance matching in high frequency lines. Fourth unit deals with the waveguides. Fifth unit deals with the RF system design concepts. So these are all the outcomes. That is upon the completion of this course. Okay. So you should be able to explain what are the characteristics of transmission line and what are the losses associated with the transmission line, and you should be able to write about what is standing wave ratio and what is input impedance at high frequency transmission lines, and you should be able to analyze what is impedance matching and how to do that impedance matching by using steps and using Smith charts, and you should be able to analyze the characteristics of TE and TM waves. And after the completion of this course, you should be able to design a RF transceiver system for wireless communication. So this is about the objective as well as outcomes. So this is about textbooks and reference books that can be followed for this subject. In Unit 1, Transmission Line Theory. So which deals with the general theory of transmission line, the general solution, and what are the primary and secondary constants related to the transmission line theory, and how to find out the voltage or current at any point on a transmission line. And with that we are going to discuss about and what is distortions, what is reflection, and what is the input and transfer impedance under open and short circuited lines. So this is about the unit 1. So in this session, here we are going to discuss what is transmission line, what are the types, and what are the primary and secondary constants. So let us see the transmission line theory. So what is transmission line? So in general, we can say that a transmission line is nothing but it's a two-port network which will connect the generator. So generator which will be there in that sending end, and the receiving end there will be load. So just to connect, and which will connect both the generator with the load, and that is nothing but your transmission line. So in case of circuit theory, and there is no need of considering that that is the transmission line. What is it? That is the transmission line. Here the length of the transmission line is very important. But in the case of circuit theory, there is no need of considering that length. But here in this case, it is necessary to consider what is the length of the transmission line, which means the distance between the generator and the load. And for the analysis purpose, it is very necessary to consider the length of the transmission line. So in general, we know what is transmission line is. So, and before going to the transmission line, first we should know what is lumped parameter and what is a distributed approach. So what is lumped parameters? So in case of lumped parameters, we can just say it as networks, where the resistance, capacitance, and inductances are individually lumped at distance point in this circuit. So that is at any point we can just able to identify a particular parameter. So that type of parameters are called as lumped parameters. The best example for this lumped parameter is filters. And second is nothing but a distributed approach. So which means the resistance, capacitance and inductance are distributed along the circuit. Each element length will have its own value and the concentration of individual parameter is not possible. So that is the main important thing in that is a distributed approach. The best example for this distributed approach is lines, that is transmission lines that can be used for the telephone messages and even the transmission of power, that is power lines, we can just call it as a distributed approach. Then what is transmission line? What is transmission line? So far we discussed is what is lumped parameter and what is distributed approach. So what is a transmission line then? So this is an we can call it as in conductors or waveguides that can be used for transmitting electric and electromagnetic waves over a long distance between transmitter and receiver. So as we discussed in general transmission lines, we can call it as two-port network that can be connected in between transmitter and receiver. So by means of that that is a transmitting, that is a conductors, we can able to transmit the electric as well as electromagnetic waves. So that is about the transmission lines. So here this the second we can say that the transmission line in other words. So the energy that can be transmitted either by the radiation of free electromagnetic waves or in the form of radio signals. So it can be contained to move or carry a various conductor arrangements, and that conductor arrangements are called as transmission lines. Okay. So next is types of transmission lines. So these are all the types of transmission lines. Open wire line, which is also called as parallel wire line. Second one is cable. Third one is coaxial lines. Fourth one is waveguides. Fifth one is microstrip. And sixth type of transmission line is optical fibers. So we'll just see one by one. So these are all the types of transmission lines. So this is a two wire line, or you can call it as parallel wire line. This is a coaxial cable. And this is an example for waveguide. There are two types of waveguides. It may be a circular waveguide or it may be a rectangular waveguide. And this microstrips and this parallel plate lines are example for the planar transmission lines. And this is a microstrip line. So here what is open wire line? So this open wire line, or we can call it as two wire line. So what is this? So it's actually a common form of transmission line. So here the conductors of such lines are considered to be parallel or separated by the air dielectric. So this is one conductor, this is the another conductor which is separated by means of air dielectric. So that is why it is called as open wire line. So two wire line, it is also called as open wire line. So the best examples as we discussed, the telephone lines, and we can just say that the power lines are the best example for this two wire line. And next one is nothing but cable. So coaxial cables. So this coaxial cables which will have two conductors. One is outer conductor, the other one is inner conductor. So why it is called as coaxial cable? So this two conductors are connected in such a way that both are coaxial in nature. So that inner conductor which is coaxially connected with the outer conductor. So that is why it is called as coaxial cables. So this coaxial cables are normally in underground lines. So for telephone lines, this consists of hundreds of individually paper insulated conductors will be there that will be twisted in pair. So combined inside a protective layer or the plastic sheath. That is nothing but a coaxial cable. And the power transmission lines which will have two conductors, but the telephone cables which will have hundreds of individual conductors within that. So each and every conductor is isolated by means of papers, so which are twisted in pair. And next one is nothing but waveguide. So as I told you, it may be a circular waveguide or it may be a rectangular waveguide. So that will be used in that microwave frequency for the principal the principle used in that waveguide is total internal reflection. Next is, this is also example for open wire line or the parallel wire line, as I told you, which will have two conductors which are separated by means of wire medium. So this is your coaxial line, or we can call it as coaxial cable, which will have both inner and outer conductors, and both these conductors are connected coaxially. That is why it is called as coaxial cable. So next one is waveguides. So these three types of transmission lines are very important. In most of the applications, we'll be using all these three types. So next comes circuit parameters. So by considering the circuit parameters, it is also called as transmission line parameters. So this transmission line parameters are broadly classified into two types. One is primary constants, second one is secondary constants. So why this transmission line parameters are classified into two types? Okay. So this primary constants are nothing but R, L, C and G, that is resistance, inductance, capacitance and conductance. And why these parameters are called as primary constants means, so all these primary constants are independent of frequency. So that is why this R, L, C and G are called as primary constants. Then what is secondary constants? Secondary constants are nothing but characteristics impedance and propagation constant. So these two parameters are also called as secondary parameters. Why? Because in both the secondary parameters Z0 and gamma, that is Z0 is nothing but characteristics impedance and gamma is nothing but propagation constant. So both are dependent on the frequency, that is frequency dependent. So that it is called as secondary. Okay, so the difference between primary and secondary is that primary constants are independent of frequency, but the secondary constants are dependent. So this is the basic difference between the two parameters. So first one is resistance. So what is resistance, inductance, capacitance and conductance? So as I told you, all these four parameters are all called as primary constants. And this resistance, first we'll just consider resistance. So what is resistance? Actually it is uniformly distributed along the length of the conductors. And this resistance depends upon the cross-sectional area of the conductor and the length of the conductor. So which will consist of both. It is depends upon the cross-sectional area of the conductor as well as the length of the conductor. So it is usually notated by the R and by the unit ohms. Next one is inductance. So what is inductance? What is that part of inductance in the transmission line? When the conductors carry current, what will happen? The conductor will be surrounded and linked by the magnetic flux. So this flux linkages per ampere of current that gives rise to inductance. So that is an effect of inductance in case of transmission lines, and which is denoted by L and the unit is Henry. Third one is capacitance. So what is capacitance? What is the effect of capacitance here? As I told you, in that open wire line and parallel wire line, since the two conductors are separated by the insulating dielectric, so what will happen? So definitely there will be a capacitance effect. So the capacitance will be distributed along the conductor length. So there is an effect on capacitance. Then what is conductance? So conductance is mainly due to the dielectric or insulators of open wire lines. That may not be perfect, or there may be a leakage current that may flow. So due to that there exist conductors. Okay. So this leakage conductance will exist between two conductors, which is usually denoted by G. And that the unit of that conductance is mho. Okay, that is just opposite to that of resistance. So this is our line of cascaded symmetrical section of impedance. So you'll be considering the transmission line as nothing but it's a cascaded section of T. It's cascaded T sections. So consider this is one T section, symmetrical T section. This is another one and so on. So this transmission lines are cascaded in terms of symmetrical sections, that is symmetrical T sections. So we can just draw the incremental for the incremental length. We can just draw the equivalent circuit of transmission line in terms of primary constants. So just now we discussed what are the primary constants R, L, C and G. So in terms of all these four primary constants, we can able to draw the equivalent circuit of transmission line. So this is series arm and again this is on series arm. So the total impedance we can call it a series arm impedance. And this G and capacitance are connected in parallel, so that we can call it a shunt admittance. So there are two parameters. One is series impedance, second one is shunt admittance. So in general, we can just denote that series impedance as R plus j omega L. In similar way, shunt admittance, we can write it as G plus j omega C. Okay. Next one is nothing but we will be considering one cascaded T section, symmetrical cascaded T section. Now we are going to find out what is the characteristics impedance for this symmetrical T section. So I am considering only one section from this. So the series of impedances I am considering it as Z1 by 2, Z1 by 2 and shunt arm impedance is Z2. Since as I told you it's a symmetrical one, so the total impedance, total series of impedance is Z1. But since it has two arms, so it has to be equally divided. So that it is Z1 by 2, Z1 by 2 and shunt arm impedance is Z2. So by considering this a single section, we can able to find out what is the characteristics impedance. So we can write it as the impedance which is looking towards the T section, we can write it as Zn, which is also is equal to Z0. Here I am considering that receiving end impedance which is terminated by its characteristics impedance. So as we know that what is infinite line? If any finite line which is terminated by its characteristics impedance, then which will act as an infinite line. We know that. So if it is an infinite line, then that input impedance of that infinite line is nothing but which is also is equal to the characteristics impedance. So that is the impedance which is looking towards the infinite line is nothing but characteristics impedance. And moreover, if any finite line is terminated by its characteristics impedance, then we can call it as infinite line. So from this consideration, so we will be considering, that is we are going to just derive the characteristics impedance from this a single symmetrical T section. So Zn, that is the input impedance of the infinite line, that is also is equal to Z0. Why? Because it's an infinite line. So therefore the input impedance is equal to characteristics impedance. That is equal to the series of impedance Z1 by 2, which is in series with the parallel combination of Z2 and series combination of this 2. So you'll be writing that combination of all the impedances to find out the characteristics impedance. And then we'll be taking that LCM and we'll be just expanding that parallel combination first and then rearranging that equation and taking LCM. Finally, we can able to find out what is the characteristics impedance for this a single symmetrical T section. So that is nothing but Z0 is equal to root of Z1 square by 4 plus Z1 into Z2. Since this is a symmetrical T section, so that we can write it as Z0 T, which is also is equal to, I am just taking Z1, Z2 common, so that we can write it as 1 plus Z1 by 4 Z2. So this Z0 T, that is the characteristics impedance of T section, we can consider as a general equation so that we can just implement for the remaining T sections. And if consider there are n such terminated sections. So likewise there are n number of sections. Consider like that. If the input and output currents, we can just assume it as input current is Is and the output current is IR, and we can just write that equation as Is by IR. That is nothing but the ratio between sending end current to the receiving end current. We can write it as E power n gamma, where n represents number of terminated sections. So n gamma, that gamma represents propagation constant. And in general, we know that gamma is nothing but, again, it consists of two more parameters. One is attenuation constant, the other one is phase constant. So therefore, gamma is equal to alpha plus j beta. So Z0 and gamma are the secondary constants of the transmission lines. So I told you the differences between primary and secondary constants. So secondary constants are dependent on the frequency, that is frequency dependent. But the primary constants are independent of frequency. Okay. Next comes the gamma value. That is, we are going to find out what is gamma in terms of series arm impedance and shunt arm admittance. So for that, we'll be considering an incremental length del x. So one section, I'm just considering it as an incremental length, and that length I'm just denoting it as del x. So for this transmission line, we can just able to write what is the binomial theorem. So by using binomial theorem, we can able to find what is the gamma value. So as we just derived, Z0 is equal to this equation, and we'll be writing that Z0, Z1 and Z2 as common, so that we can write this equation like this. Okay. Now from this diagram, we can able to write what is Z1 and what is Z2. That is what is series sum impedance, what is shunt arm impedance. So Z1 we can write it as Z into del X. Similar way, Z2 we can write it as 1 by Y del X. So impedance, here it is admittance. So that we can write it as 1 by admittance. Now we can just substitute Z1 and Z2 in this equation as it is, and simplifying this equation, get this equation as Z0 is equal to root of Z by Y. Okay, so characteristics impedance in terms of series sum impedance and shunt of admittance. So we can substitute Z0 is equal to, actually we know that Z is nothing but R plus j omega L and Y is nothing but G plus j omega C. So the secondary constant value in terms of primary constants. Similar way, we can able to derive what is gamma in terms of primary constants. So for that, what we are going to do is, so we are going to take that Z0T equation and we are going to use the formula binomial theorem. By using that binomial theorem, we are going to expand it. And we know that binomial theorem 1 plus x power n is equal to 1 plus nx plus n into n minus 1 by 2 x square and so on. So just we are going to substitute in the binomial theorem and finally we are able to find what is gamma. So this is our expansion of binomial theorem. We are just expanding it. And now we are going to apply, and since we are just taking that incremental length of the line del x, so that we can write it as z1 is equal to z into del x as we just substituted in the previous derivation. Here also we are going to consider like that, and z2 is equal to 1 by y del x. And the propagation constant, and that can be applied as gamma into del x. Now in this equation, we are going to substitute e power gamma del x. So here we are going to write wherever the gamma, we are going to replace it as gamma del x, and wherever there is an z1, that can be replaced it as z into del x, and wherever the term z2, that can be replaced it as 1 by y del x. So just substituting all these three values in this equation, we can able to find this equation. Okay. Now we can just equate with the binomial series. So e power gamma del x 1 plus, I am just replacing this as gamma into del x. In this thing, I'm just writing it as gamma square. And here, instead of this one, I'm just writing it as gamma cube and so on. So this del x square, del x power 3, del x power 5 as it is. So using this formula, I'm just comparing this so that we can write it as what is equal to, it is root of z into y. So by comparing both this equation and dividing by del x, finally we can able to find what is gamma. So that's nothing but root of z into y. So where gamma is nothing but propagation constant. Okay. So please make a note. So this is the value for the line of distributed constants. And here since all the elements lengths are alike, so we can just, since z and y are in terms of unit length. So therefore the gamma value also per unit length of the line. Okay, so likewise we can able to find what is the characteristics impedance and propagation constant of the transmission line. Okay, thank you all.